Swayam Prabha. Digital India. Educated India.
Okay. So, having understood that part of motion, let us look at total motion of a point of a rigid body. So, let us say I have a rigid body. I am only going to talk about planar, and it is easily extendable to 3D motion. Okay. So, let us say we will take 2 points as we did earlier. There were many points that we took. We can take just 2 points to illustrate the motion. Let us say this is A, this is B. As we said earlier, let me make it a simple rigid body so that I can draw again easily. Okay, so let us say, okay, and let us say this has gone through a rotation like this and a translation. Let us say this is A and this is B. So, as you can see, this is the motion that A has undergone, this is the motion that B has undergone. Alright. Now, whenever we talk about motion, we cannot talk about motion unless pure motion, unless we know there is one reference which is not moving, alright, or in other words I have to have what is called a fixed frame. I am not going to go into details of what a fixed frame is. Assume that this is a fixed frame. Any fixed frame we are going to use capital letters, okay, say X and Y, or I capital and J capital. Okay. When I put a wiggle here, it means vector. Okay. So, I have a unit vector along this direction which is I, a unit vector along Y which is J. K will be outward unit vector. Okay. Now, with respect to this, it is possible for me to define each of this. Let us say this is t equal to 0, okay, and this is say t equal to t1, just giving you some example. Okay. It is possible for me to track the motion of this particular body. If I have to find out what is this position, I should first know the position with respect to the fixed frame, the initial position. Okay. So, let us say this is RB current. So, let me just put an RB naught. If I add that to R, this is B going from 0 to T1, then I can find out the complete motion of this particular body, this particular point B, right. So, let me call this as RB at time T1. Okay. I seem to be complicating it a little bit, but the understanding is simple. I describe a point on this body at a reference time t equal to t naught or 0, okay, with respect to a fixed frame of reference. I have an I and a J, capital I and capital J denoting the fixed frame of reference. Later on we will understand why we are using capital letters for these. Okay. And therefore, I can describe this particular point as well as this particular point. This is the motion that has taken place, this is the original, RB naught is the original position. Okay. And in a similar way I will be able to find out RA naught, which is this, and RA taken from 0 to time t1. Okay. So, that will represent the position of A at t1. Okay. For now, let us just make it simple. I just need to know the position of B. From the position of B, can I find out the position of A? That is the question I am going to ask. Okay. knowing the current position of B, how do I find out the current position of A? So, in order to answer this question, we did an exercise over there trying to understand how the motion has occurred. Okay. Basically, I can look at this as a motion that has occurred as if there is no rotation. Okay. So, let us say something like this has occurred. These two are parallel to each other. Let me just make it look as if it is the same rigid body. So, this rigid body has undergone a translation. So, what do I understand by translation? This particular vector that represents the translation, if used here, will tell me where the point A is. So, let me call this as A prime, B prime. B prime is the same as B, because I have used B as the reference for translation. If I use the same vector that takes it from this time t equal to 0 to t1 for A, I will get to A prime, okay, which is describing a translatory motion. Okay. And then as we did in the earlier exercise, if I pivot about this particular point and rotate, I will reach this particular final configuration. Okay. So, now I know how to find out the position. First, I locate the position of B. Once I locate the position of B, then I will find out what is the position of A with respect to B. Okay. How do I write that? The position of A can be found out by position of B plus position of A, but now with respect to B. Okay. If I know the position of, so what I mean is I can go from this point through this to this, or I can go to this point, go to this point and then translate to this. Okay. And that is what I am going to do. Okay. That is what this means. If I can locate the motion of point B, and if I know what is the relative location of A with respect to point B, I have solved the problem of finding out what is the position of A. Okay. Now, what is this going to be? I have already done a translatory motion. So, this will not involve translatory motion, this will involve only a rotational motion. Is that clear? So, once I introduce the rotational motion over here, I have solved the problem. Okay. So, pictorially, if this is the location of B or B, I have put a vector symbol over here because this is a position vector. Given the position vector of B and the relative location of A with respect to B, I can find out the location of A. That is basically what this means. Okay. Now, how do I find out the velocity of B? It is nothing but the time derivative of RB, right. What is the velocity of A? It is the time derivative of A. So, velocity of A equals time derivative of A. It is very important that I look at this as a time derivative of the vector. Okay. Similarly, velocity vector of B is nothing but time derivative of the position vector of B. Okay. So, if I can find out the relationships between VA and VB, again I will be able to write down, given the velocity of B, what will be the velocity of A. Okay. So, in this particular exercise if I do that, r dot of A is nothing but r dot of B plus r dot of A with respect to B. Okay. This can also be written as VA equals VB plus V of A with respect to B. If it is a pure translation, what do you know of this? Is A translating with respect to B? Let us look at that. Supposing it is a pure translation, which means that it remains the same. This is B, this is A. Okay. Let us say it has gone through this by going through some other configuration. So, it will, let us say it is going like this and then moving to this. Okay. What do you see as this vector? Remember, this vector is not like a position vector. Is this vector the same as this vector, is the same as this vector? The answer is yes, because it is a rigid body that we are looking at, or in other words, if it is going through a pure translation, the derivative which shows that there is a change that has occurred in this particular vector has to be equal to 0, or in other words, the velocity of B and velocity of A will be exactly the same if it is a translatory motion. Is this clear? And therefore, this indicates that I first do a translatory motion. Supposing this were non-existent, if this were non-existent, VA is equal to VB implies that there is a pure translation involved. Okay. Automatically that means this is nothing has to do with, so this is just pure translation, and this involves, supposing this were not the case, it was something like this, like what we have done earlier. If I had taken all through like this and reached this particular point, it would have been something like this, and then after this I have to do a rotation. So, you can see that this involves just angular velocity. So, you have an angular velocity here and a translatory velocity over here. Okay, that is how we understand this.